Hi friend, welcome all to my educational channel Math A to Z. We already know that S3 is a symmetric group of degree 3. That is, S3 is a group of all permutation of 3 symbols. Three symbols. Also, we know that A3 is a group of all even permutation of 3 symbols. That is, A3 is a subset of S3 because it contains all even permutation and it contains all the permutation of 3 symbols. So A3 subset S3. Also A3 together with the multiplication of permutation is a group. This type of group is called subgroup because A3 is a subset of S3. Here S3 is a group and A3 is itself a group. So we say that A3 is a subgroup of S3. Now, generally we write the definition of subgroup as, let G circle be any group and H be a non-empty subset of G, non-empty subset of G. If H circle is also a group, then H circle is called a subgroup of G circle. Right? This is the definition of subgroup. Now we know that only identity element, if we take only identity element in a set, then this is a subset and this subset together with the composition is a group. Also, G is itself a subgroup of G. So, G circle is a group. That is, this is a subgroup and this is also subgroup and this is the subgroup of G circle and this is also the subgroup of G circle because this and this are 2 groups and this subgroup is called trivial subgroup. And this subgroup where the group itself, the subgroup of the group is improper subgroup. improper subgroup, and all the other subgroup which are not trivial and not improper are called proper subgroup. Proper subgroup. And here we see, or we say first, A3 dot is a proper subgroup of S3 dot, and this is also important to say that S3 dot is a non-commutative, but A3 is a commutative. So this is the example of a commutative subgroup of a non-commutative group. So many examples of subgroup, like Z plus is a group, and if we take 2Z plus, this is also a group. So this group is called the subgroup of Z plus. And not only 2Z plus, if we take MZ plus, these are all the subgroup of Z plus. Also, if we take the group as R star dot, where R star is equal to R excluding 0, and Q star dot, where Q star is also Q minus 0, and this is also a subgroup of R star. Okay, so there are so many examples of subgroup. Important to notice that if in a group G circle EG be the identity element and H circle be a subgroup of G circle, then in H circle EH be the identity element, then we must have EH and EG are same. Okay, so in the form of theory we say that in all subgroup the identity element is the identity of the group. Okay, now we prove this result. From the definition of EG, we say that for all A belongs to G, EG compose A equal to A compose EG equal to A. Also, from the definition of EH, we say that for all H belongs to H, H compose EH equal to EH compose H is equal to H. Now, if H belongs to H, then obviously it is belongs to G also, because H is the subset of G. Then we put H in place of A, because H is also belongs to G. That is, we write EG compose H equal to H compose EG equal to H. Now from this relation and this relation, or this relation and this relation, we get EG compose H equal to EH compose H. Or we can write H compose EH equal to H compose EG. Okay, from this and this, or from this and this. Now here, if we apply right cancellation law, or here if we apply left cancellation law, then we get EG equal to EH, or this is gives the same result, EH equal to EG. Okay, so we say that the identity element is the identity of the group in all subgroup. Go to another important property of inverse in group and inverse in subgroup. Let A belongs to G and the inverse of A in G is A dash, and this is also belongs to G, and let this A is also belongs to H. A belongs to H, and here we take A double dash be the inverse belongs to H. Now from the property of inverse we get A compose A dash equal to A dash compose A is equal to E. Also from H we get A compose A double dash equal to A double dash compose A equal to E, because the identity are the same in the group and the subgroup also. Now clearly from these two relation or from these two relation we get A compose A dash is equal to A compose A double dash, because this result is E and this result is also E, and by left cancellation law we get A dash is equal to A double dash. Similarly by right cancellation we get A dash equal to A double dash. So we can say that the inverse of any element is same as its in group. Here is three important theorem to easily prove a non-empty subset of a group to form a subgroup of the group. Now we state all the three theorem and its proof one by one. The first theorem is, let G circle be a group and a non-empty subset H of G forms a subgroup of G if and only theorem. If and only for all AB belongs to H, A composition B belongs to H, and for all A belongs to H imply A inverse belongs to H. That is, if H circle be a subgroup, then this and this hold, and if these two property hold, then H circle is subgroup. Now we first take H circle be a subgroup of G circle. Then clearly H circle follow all the property of group, because this is a subgroup, that means it's a group. So clearly the first property is the closure property of group, that is first property hold, because it is a group so it is closed, that is for all AB belongs to H, A composition B belongs to H. Also second property is the inverse property, because in a group for all A belongs to H, A inverse must be belongs to H. So the second property is also hold. That is, if we take H circle be a subgroup, then it is easy to see the first and second property. Now conversely, let 1 and 2 hold for non-empty subset H, for H not equal to 5 subset of G. We have to prove using first and second H follow all the four property of group. That is, here 1 is closure, that is closed, 2. This is associative because we know that associative is hereditary property, and we know G be a group, so it follow the associative property, and since the mother set follow the associative property, so all the subset must follow the associative property because of heredity. So the associative property called associative. And in 3, we have to prove identity, but 4th property here given inverse, because for all A belongs to H, A inverse belongs to H, so this is the inverse property. Now we take A belongs to H, we get A inverse belongs to H, and in place of B, if we take A inverse, then we get A inverse belongs to H. This must imply A composition A inverse belongs to H because of 1. So A compose A inverse, this means E belongs to H, and this is the identity of H. So identity property is also hold. Identity property is also hold in H. So closure, associative, identity and inverse. All the 4 properties of group are hold. So we say that if 1 and 2 hold, then H circle must be a subgroup of G circle. Now we go to the second theorem as theorem 2. G circle be a group. A non-empty subset H of G forms a subgroup of G if and only for all AB belongs to H imply A composition B inverse belongs to H. Here is also if and only theorem, and here 2 property in first theorem. This is the closure property and this is the inverse property is in compact form or nothing. AB belongs to H imply A composition B inverse belongs to H. Now we prove this theorem as we first take H circle be a subgroup, then it must follow closure, associative, identity and inverse, and for all AB belongs to H we must have A B inverse belongs to H because of inverse property. B belongs to H, then B inverse also belongs to H, and A B inverse both belongs to H gives A composition B inverse belongs to H because of closure property, right? So if we take H circle be a subgroup, then it is easy to see A composition B inverse belongs to H for all AB belongs to H. Now we prove the another part, that is we here take for all AB belongs to H imply A composition B inverse belongs to H, and we have to prove that H circle be a group or a subgroup of G. That is, we have to prove H circle be a group. So all the 4 property we have to see here. At first, let A belongs to H, and we write A 2 times belongs to H. Then from the given property, it is clear that A composition A inverse belongs to H. That is, E belongs to H because A composition A inverse is equal to E. So this is the identity element, and this implies identity. identity property, identity law in H. Now if E belongs to H and A belongs to H, then E A belongs to H, this implies E compose A inverse belongs to H, and this is imply A inverse belongs to H. That is, for all A belongs to H, we get A inverse belongs to H, and this is the inverse property. Inverse. Now we take A belongs to H and B belongs to H. This implies A B inverse belongs to H by using the inverse property, and this gives A composition B inverse whole inverse belongs to H because of the given property. If AB belongs to H, then A compose B inverse belongs to H, and here we get A B inverse belongs to H, then we get A composition B inverse whole inverse belongs to H, and this gives A compose B belongs to H, and this is closure property. This is closure. And the last property, the associative, it's not required to show because associative property hold in the mother set, that is in the group G, so it must hold in the subset because it hereditary property. So we first see identity, then inverse, then closure, and we say this is also associative property called. So H circle must be a subgroup of G circle. Now we go to the third theorem and also the last theorem of the class. The statement of the third theorem is G circle be a group and H circle be a non-empty finite subset of G. This is very important, finite. Then H circle is a subgroup of G circle if and only for all AB belongs to H, imply A composition B belongs to H. Now go to the proof. Here this is only if and also if and only theorem. If we take first H circle be a subgroup, then by closure property we easily say that for all AB belongs to H, A composition B belongs to H. It is whole. Okay, so the first part is very easy. That is, if we take this is a subgroup, then this is the closure property. That is this proved. Now we take conversely that for all AB belongs to H, A composition B belongs to H, and here F is finite. So H is finite set, finite subset of G, and for all AB belongs to H, imply A composition B belongs to H hold. That is the closure property hold. Now we have to show that H circle is a subgroup. That is another three property required: associative, inverse, and identity. So we let any element H belongs to H. Then by the closure property, H square, H cube, H4 to HR, HS to this all belongs to H. Here R, S, these are positive integer. and here we take S greater than R. Now since H is finite, so H square, H cube, H4 and these sets or these all the elements must not unequal, because if all the elements are unequal or distinct, then H must be infinite. So we must have there exists I, J belongs to N such that H to the power J equal to H to the power I, and we take J greater than I here. Now this relation gives H to the power J minus I is equal to E, right? And J minus I is greater than 0. Also J minus I belongs to natural number. So H to the power natural number must be in this line, that is must be in the set H, and the value of H to the power J minus I is the identity element. So the identity property must belongs to H. So identity property hold. That is, we first get closure and second we get the identity property. Now here we see that J minus I, this is J minus I. J minus I greater than 0. That is, we can write J minus I greater equal to 1 and J minus I minus 1 greater equal to 0, and we write this relation as H composition H to the power J minus I minus 1 is equal to E, and this can be also written as H to the power J minus I minus 1 composition H is equal to E, and from this relation we must say that the inverse of H is equal to H to the power J minus I minus 1, and this is belongs to H. Here H be any element of H, and we see that the inverse of H belongs to H. So the inverse property is also hold. Now here is no need to see the associative property, because H be a subset of G and G be a group, so here must follow the associative property. So by hereditary law we say that H circle must be follow associative property. So here closure, here identity, and here inverse, and also associative. All the four property of group must satisfy. That is, we see that H circle be a subgroup of G circle if for all AB belongs to H, A composition B belongs to H, and here must be H is finite. Now we get at the last of the class an important example to see if H is not finite, then it may not be a subgroup of G circle. If we consider G as Z together with respect to plus, that is G circle is equal to Z plus, and if we take H is equal to N, that is the set of natural number, and this is obviously infinite set, and with respect to plus, n plus must be closed, because we know that for all AB belongs to n, A plus B belongs to n. Addition of two natural number is also a natural number. But we already know n plus is not a group, because the inverse of any element does not exist, and the identity element is not here, because 0 be the identity of Z plus, and here is 0 does not belongs to n. So this is not a group, and this is the important example to show that if H circle is not finite, then it may not be a group. Okay, thank you for watching. Thank you very much.